Thanks for the introduction. It's nice to be here in Australia where it's all tropical and nice. But yeah, so today I'll tell you about some new bounds on quantum metrology and a rather general noise model. And this is joint work with Robert Lazenby, who used to be a particle physicist at Stanford. On the other hand, I come from more of a quantum information, quantum computing background. So in this talk, you'll see some more mathematical results that are rigorously proven, but hopefully you'll also leave for lunch with some high-level physics takeaways. And if I have time, I'll also talk a bit about how quantum error correction can be useful in quantum metrology and some related future directions. Now, I should also say that you should feel free to interrupt me at any point if you have questions. In particular, I was at QIP last week, and then I flew back to SF, and then a few hours later, I flew here for 15 hours, so I'm quite tired. And so yeah, just interrupt me if I start saying nonsense. Okay, so what is quantum metrology? Well, broadly speaking, the aim of quantum metrology is to make highly sensitive measurements of physical parameters. More concretely, a canonical task would be to estimate one or more parameters characterizing the Hamiltonian of some system. So we imagine we have some detection system. It's subject to some physical influence in that there's terms in the Hamiltonian describing that physical influence that we want to measure. So we want to estimate parameters like the corresponding parameters in the Hamiltonian. Example applications of quantum metrology include magnetometry, gravitational wave detection, such as with LIGO, and axion dark matter detection. Okay, so where does the quantum come into quantum metrology? Because metrology is just the study of measurement. Well, on the one hand, as we're familiar with things like the uncertainty principle, quantum mechanics sets fundamental limits on how precisely we can make measurements. And in this talk, we'll derive some new quantitative limits of this kind in a more general setting. And on the other hand, we can sometimes take advantage of quantum mechanics, such as by using entanglement to make higher precision measurements than would be possible with quote unquote classical methods. So for example, LIGO has already used squeezed light, which is a non-classical state of the electromagnetic field. And this has significantly improved the precision. Okay, so for this talk, we're mainly going to focus on the problem of estimating a single parameter, which we'll denote by G. So we imagine that the form of the Hamiltonian is completely known to us, except when it comes to the value of this parameter. For instance, in the examples we had on the previous slide, in magnetometry, G might represent the magnitude of the magnetic field. In gravitational wave detection, G could represent the gravitational wave amplitude. In axion dark matter detection, G might be the amplitude of the axion field. So in many cases, like in these last two examples, we can often think of G as a very, very small parameter, but more generally, we'll be interested in measuring G very precisely. So now in the simplest setting, when there's no noise and the detection system is just evolving unitarily under the Hamiltonian, the question of just how precisely we can measure G is a basic one that was resolved many, many years ago. However, in realistic, more practical settings like actual experiments, we can't treat the evolution as unitary because there's going to be noise acting on the detection system. It's coupled to this complicated environment that we can't control nor precisely keep track of. On the other hand, the fact that the environment is really complicated can actually also help us because we can often approximate its effects as Markovian or memoryless, meaning like the coupling between the system and environment at one time doesn't depend on what happened at previous times. So the main assumption we're going to make is that the noise acting on our detection system is Markovian. And this is a pretty general assumption, like Markovian noise is actually a fairly generic feature of complicated, strongly coupled environments where like the mixing time of the environment is much shorter than the coupling time between the system and environment. So the effects of the environment will look memoryless to a very good approximation. Okay, so more precisely, we'll formalize this assumption of Markovian noise by assuming that the state rho of our detection system is evolving as described by a Markovian master equation, which is also known as a Lindblad master equation. So here, the LJs are Lindblad operators, which capture the effect of the interaction with the environment. As an example, for a harmonic oscillator that's damped by its coupling to a Markovian environment, we just have one Lindblad operator, which is proportional to the annihilation operator. And this is actually a very physically relevant example, which we're going to come back to later. But for now, just some important notation to keep in mind. So throughout the talk, we'll use dots to denote derivatives with respect to the time t, like with rho dot here in the master equation. And we'll use primes to denote derivatives with respect to the parameter g. So by default, you should think of everything we'll encounter, including any scalars or operators, as functions of both t and g. Except for the purposes of this talk, we'll assume that the Lindblads only depend on time. In the paper, we analyze the more general case where they can also depend on g. Okay, so for instance, the state rho of the detection system is obviously evolving with time, so it depends on g, but it evolves under this master equation, and which is different depending on the value of g in the Hamiltonian. So the state rho also depends on g. Okay, so we want to determine how well we can measure g in this setting of Markovian noise, and how can we quantify this? The way we'll quantify this is via the quantum Fisher information, which is a central quantity in quantum metrology. But for those of you who don't necessarily work on metrology, an intuitive way to define the quantum Fisher information is actually in terms of the classical Fisher information. So let's look at that first. The classical Fisher information is defined for one parameter families of probability distributions. So let's say we have a family of distributions parameterized by g. And to clarify here, so for each fixed value of g, P of g denotes a probability distribution over some outcome space. So for example, this might represent a distribution over measurement outcomes. Like let's say we're measuring some system whose state depends on g, then we get a different distribution P of g for different values of g. Okay, now for any two distributions, the relative entropy or KL divergence d quantifies how distinguishable the two distributions are. And since we care about estimating g very precisely, we want to know how well we can distinguish between two very close values of g. So let's consider the relative entropy between the distributions parameterized by g and g plus delta g. If we expand this around delta g equals 0, then the leading term is the delta g squared term, and its coefficient is given by the classical Fisher information. Okay, so why is the leading term the quadratic term? Well, the 0th order term vanishes because when delta g equals 0, the two distributions are just the same, so the relative entropy is 0. The first order term also vanishes because the relative entropy is always non-negative. So because it's 0 at delta g equals 0, we can't have a linear term because then otherwise it would go negative for small negative values of delta g. Okay, so the classical Fisher information captures the leading order behavior of the relative entropy for very, very small changes in the parameter g. And one useful implication of it is the Kramer-Rao bound, which lower bounds the variance of any unbiased estimator of g in terms of the inverse of the classical Fisher information. So this tells you the larger the classical Fisher information, the more precisely we could measure g. Analogously, the quantum Fisher information is defined for a one parameter family of states, rho of g. So for instance, this could represent the different states of our detection system, depending on the value of the parameter g in the Hamiltonian. And as I was saying, if we do some measurements on the system, then we get a probability distribution over measurement outcomes. This distribution is parameterized by g because the probabilities depend on rho of g. So for any measurement scheme, there's an associated classical Fisher information. The quantum Fisher information is then just the maximum of this classical Fisher information over all possible measurements we can do, so all possible POVMs. Oops. And as you might expect, there's a quantum analog of the Kramer-Rao bound, which bounds how well you can estimate g by measuring rho in terms of the quantum Fisher information. Okay, so now let's analyze the quantum Fisher information, or I'll call it the QFI for short, in our setting of arbitrary Markovian noise. How do we do this? Well, first we do a bunch of algebra to obtain this equation for the time derivative f dot of the QFI. And this equation is in terms of h primed, which is, remember, the g derivative of the Hamiltonian, as well as the Lindblad operators, and also this quantity script L, which is related to the g derivative of the state rho. So you really shouldn't worry about any of the details here. The point is just to illustrate that we use our assumption of Markovian noise to get this expression for the QFI growth rate, which depends on h primed, as well as the Lindblad operators. Now, to further proceed, we're going to write h primed in terms of the Lindblad operators in this form, where the beta j and gamma jk are scalar coefficients, and capital G is an arbitrary Hermitian operator. So I want to emphasize here that we can consider any arbitrary decomposition at this point, because there's no restriction on what this operator G can be. In other words, you're free to choose any values for the coefficients beta and gamma that you'd like, and then you just take G to be whatever's still left over in h primed. We'll look at which distributions are actually useful later. But for now, for arbitrary beta and gamma, we substitute this decomposition back into our equation for f dot, and then we can eventually arrive at this upper bound on f dot by doing some more algebra, applying Cauchy-Schwarz a couple of times. So to explain this bound, here the AJ each AJ is this operator, which depends on the beta and gamma coefficients that we chose, as well as the Lindblad. And f sub g is a quantity which depends both on rho and on g. It's sort of like the variance of g, but it's convex in the state rather than concave. So more precisely, f sub g over 4 is equal to the variance of g with respect to rho whenever rho is a pure state, but then it's concave for mid-state. It's convex for mid-states. Sorry, did I say concave? I meant convex. So why does this quantity f sub g make sense in the context of our bound? Well, for one thing, it's known that in the noiseless case, when the detection system is evolving unitarily, so it stays in the pure state, the form of the QFI, or the QFI growth rate, just depends on the variance of h primed. And here, if we were in the noiseless case, then we wouldn't have any Lindblad operators. So G would just be h primed, and we wouldn't have these AJ terms. So our bound would indeed reduce to the correct form in terms of the h primed when there's no noise. But now more generally, it's intuitive that you can't get a better QFI by using a mixture of states rather than just by using the best pure state in that mixture. In other words, the QFI or any bound on it should be convex in the state rho. And indeed, f sub g is convex, whereas the variance would be concave. So like for pure states, it wouldn't matter whether we used f sub g or the variance, but because we're in the noisy setting where, even if we start in a pure state, it might evolve into a mid state. So we often care about mid states. It's important that we get this tighter characterization in terms of f sub g. Okay, so for any choice of the coefficients beta j and gamma jk, we get this upper bound on the QFI growth rate in this form. So of course, we get the tightest bound by minimizing over all possible values of the coefficient. So far, this bound can look pretty abstract. We'll see some examples of how it can be usefully applied in concrete settings later. But first, let's look at some of its general features. So I'll start with some sort of basic features, and then I'll talk about some nice features, like how it leads to tighter bounds than in previous work. First, as we've already basically observed, this bound is convex in the state rho, as you should expect for the QFI. As I said, f sub g is convex, and of course, this expectation value of the AJ dagger AJ terms is linear in rho, so it's trivially convex. But at this point, you might start to worry because these quantities depend on rho. So like, how do we actually apply this bound? Because if we had to solve for rho as a function of time using the master equation, then this could get pretty complicated. Well, in many cases, it's simple to get a state independence bound on the QFI. For instance, we could upper bound these two state dependence terms, the f sub g and the AJ dagger AJ sum, in terms of operator norms. And this is going to be valid as long as the norms are bounded, which they will be for any finite dimensional system, for instance. But in many other cases, instead of looking for a completely state-independent bound, it might be more useful to ask for a bound that holds for some physically relevant class of states. Like, for example, if our detection system is a harmonic oscillator, then in some settings, the QFI growth rate can actually be made arbitrarily large by just using states of higher and higher energy. So a state-independent bound wouldn't even be meaningful in this case. Instead, we might want to say, let's impose some upper limit on the average energy and ask, what's the largest QFI that we can attain using states under this energy threshold? And we can get this from our bounds by just analyzing F sub G and the AJ dagger AJs for this restricted class of states. Okay, another feature of the bound is that it depends explicitly only on H primed rather than on the full Hamiltonian H. So remember, H primed is the G derivative of H. And so this is useful because in real experiments, there's often a lot of complicated stuff going on to control the detection system. But anything you do that's independent of this unknown parameter, G, it'll only go into H and not into H primed. You might also imagine doing some kind of adaptive procedure that does depend on G, like making intermediate measurements followed by classically controlled feedback. But by the principle of deferred measurement, these are equivalents to applying some controlled quantum gates, in other words, unitary evolution, followed by measurements at the very end of the circuit. So again, you can just subsume all of these things into H without affecting H primed. Okay, another thing that can make this bound look abstract is this optimization over the beta J and gamma JK coefficients. And also these coefficients are allowed to vary with time as well. So for some systems of interest, it turns out you can actually do this optimization analytically. In general, you can always try to do the optimization computationally. But in fact, it turns out that even simple, potentially non-optimal choices of these coefficients actually give rise to general bounds on the QFI that are tighter than any bounds in previous work. So previous bounds applied only to finite dimensional systems that are time independent. So we'll consider that setting for the sake of comparison. And by time independent here, we mean that H primed and the Lindblad operators are time independent. Obviously, the state is still evolving with time. So here I've plotted in magenta a bound on the QFI that you can get from our general F dot bound by making a rather simple, not necessarily optimal choice of the betas and gammas. And this is for the case where H primed can be decomposed into Lindblad operators. So remember, we decomposed H primed in this form, where G can be anything. So this is the case where G can be set to 0 if you want to. In other words, H, sort of colloquially, H primed is in the Lindblad span. Okay, so you can see from the bound, from our plot that our QFI bound grows quadratically with time at first, and then eventually becomes linear. And we can understand this by looking at our bound in pink. So at small times, the QFI F is going to be small because we just started the experiment. We haven't accumulated much information yet. So this means that to make the right-hand side of this bound small, in order to get as tight of a bound as possible, we might as well choose the betas and gammas to be small and basically put all of H primed into G. Because with this choice, the second term with the AJs will be small, whereas F sub G could be large, but you don't care because F is small. So we basically just have the first term with G set to H primed, and integrating this, we get that at small times, the QFI grows quadratically with time, or the QFI bounds grows quadratically with time, with coefficient set by FH primed. Now, at the other extreme of large times, we should expect that the QFI is large, at least if we're doing our experiment right. So we want to make F sub G small in the bound. And since we're in the case where we can set G equals 0 if we want to, we might as well do that and make F sub G 0. So then we're just left with the second term, which integrates to a linear time dependence. So by comparison, prior work gives this looser linear bound in blue, which obviously doesn't capture the initial quadratic growth. I've also plotted the best bound we can get if we try to use existing methods to derive an initial quadratic bound, but you'd only end up with this gray bound here, which is the same quadratic at all times. Okay, so the reason that previous work leads to these looser bounds is essentially because they rely on discretizing the time evolution into many identical steps, and then use known bounds on the QFI accumulated over a large number of identical operations. And the way these bounds are constructed essentially requires not only applying the same operation at each time step, which is why previous results only apply in the time independent setting, but crucially, these bounds also effectively use the same decomposition of H primed at every time step. By contrast, we directly analyze the time derivative of the QFI starting from the master equation, and this enabled like a fully continuous time-dependent treatment that allows us to easily vary the decomposition of H primed with time. And this approach pays off because, as we can see, in order to get the correct parametric behavior at both small and large times, it's important that we vary the betas and gammas with time so that we can appropriately trade off between the two terms in our F dot bound. Now, in the other case where H primes can't be decomposed purely into Lindblads, in other words, we can't set G equals 0, or H primed is not in the Lindblad span, the QFI bound grows quadratically for all time. It's actually a faster quadratic at short times and then a slower quadratic at large times. And again, we get this bound that's tighter than previous work via a simple, not necessarily optimal choice of the betas and gammas. So similar to the previous case, where H primed was in the Lindblad span, we get this bound by tuning the betas and gammas such that G is large at large times, and then gets smaller as the QFI F increases. But unlike in the previous case, where we could set G equals 0, so that we just have the second term at large times, here we can't set G equals 0. So the first term in the bound will always be there, which is why the large time behavior is still quadratic to leading order. Okay, so as an aside, what's the intuition for this qualitative difference between when H primed is in the Lindblad span and when it's not in the Lindblad span? Well, intuitively, it's essentially the fact that when H primed is not in the Lindblad span, you can always find a component of the signal that's sort of perpendicular to the noise or distinct from the noise. So as a simple example, let's consider if we're in the 1 qubit case and we're trying to detect the strength of a Pali-Z forcing. If we had a Lindblad operator that was also proportional to Pali-Z, then it'd be harder to distinguish the signal from the noise than if we had a noise term that was in a difference direction. So it turns out that in higher dimensions, the appropriate generalization of sort of in the 2-dimensional case, whether your noise is parallel to your signal, is whether H primed is in the Lindblad span as it's defined here. So we've seen that our bound is tighter at all times in the finite dimensional time independent settings considered by previous work, but it also applies more broadly than previous methods. It naturally allows for time dependence and also lets us handle infinite dimensional systems, whereas previous methods essentially rely on using operator norms. In addition, we conjecture that our bound is actually tight in the sense that it can actually be attained at all times, at least if we have noiseless and SOLAs. So we show that this is true for the damped harmonic oscillator example, which I'll talk about a bit now. And this is actually an example that illustrates a lot of these points. So it's a system of practical interest that's infinite dimensional, can have time dependence, and we can show how the bounds can be exactly attained using practical classes of states. Okay, so once again, this is the master equation for a damped harmonic oscillator. So we have one Lindblad operator that's proportional to the annihilation operator. And let's consider a linear forcing whose amplitude is the unknown parameter g. So here H primed is linear in the creation annihilation operators. And note that here I've only specified H primed and not the full Hamiltonian H, because remember the bound depends only explicitly on H primed. So the full Hamiltonian H can have whatever additional G independent terms that you'd like, but we'd still get the same results. Okay, so for this system, which describes many physical systems of interest like gravitational wave detectors, we can actually get a useful state independent bound for the large time behavior of the QFI. So why is that? Well, in this case, we have that H primed is in the Lindblad span. So we can set G equals 0. So that means to get the tightest large time bound, we should just set G to 0 when we decompose H primed. And then this bound scales linearly with time with the coefficient set by the AJ dagger AJ terms. Here we only have A1 because there's only one Lindblad operator. And it turns out that A1 dagger A1 is proportional to the identity. So this leads to a state independent bound. This bound holds for all times, but it's only going to be tight at large times. For small times, remember the initial QFI growth rate is governed by F sub H primed. And for the oscillator, it turns out that F sub H primed is proportional to the variance of the momentum operator. And so this variance of the momentum operator can in turn be bounded in terms of the oscillator's energy using this inequality that we can derive from the uncertainty principle, where here n in brackets denotes the average occupation number. So putting all of these things together, we get that we can bound the short time QFI growth rate in terms of the energy of the oscillator. And moreover, this bound on the momentum variance in terms of the oscillator energy is saturated by squeezed coherent states, which implies that, at least at small times, the largest possible QFI for any given energy cutoff is attained by using a squeezed coherent state. And this is essentially what they started doing in LIGO. So like squeezed coherent states are relatively easy to prepare, but then our bound shows that this is actually the best that you can do. And okay, another interesting point is that if we restrict to states with momentum variance at most half, then it turns out we can attain our corresponding QFI bounds exactly by using coherent states, like not squeezed. We give a protocol that explicitly does so. So basically the idea is for a certain amount of time, you just let it evolve unimpeded, but then past a certain critical time, you need to like couple it to some noise less than still less to sort of move out the information. And this protocol attains the bound at all times. So since our bound is state independent at large times, this means that regardless of what state you might use, like regardless of what its momentum variance is, you can't do better asymptotically than by just using coherent states. Using non-classical states would only improve the short time QFI growth rate. However, it turns out that in other metrological settings, using non-classical states can help you, even asymptotically. So in particular, so far we've only been considering the scenario where there's a single unknown parameter G, but in many realistic settings, there might be multiple unknown properties of the signal. For instance, in gravitational wave detection, we might take G to be the amplitude of the wave, but we also don't know like its frequency, direction, polarization, and so on. But often there's a particular aspect that we're most interested in. Like for instance, in axion dark matter detection, we want to know whether the wave is there at all. In other words, whether G is non-zero. So an interesting question is, how well can we determine one parameter despite not knowing the values of others? So as a prototypical model, we can imagine we're interested in the amplitude G of the forcing on a damped harmonic oscillator, but we also don't know the frequency omega of the forcing. And harmonic oscillators serve as a good model for both gravitational wave and dark matter detectors. So recall from the previous discussion on the harmonic oscillator that if the frequency were known, then we're able to obtain this state independent bound F dot max for the maximum QFI growth rate. And this bound can be attained asymptotically using coherent states, whereas we can't do any better by using non-classical states. However, in the case where the frequency isn't known, then by using coherent states, you can only attain this peak sensitivity over a small frequency range, delta omega, that's set by the damping rate. Now, if you instead use non-classical states, like squeezed coherent states or Fock states, they can't improve the peak sensitivity, but they can expand the sensitivity bandwidth, meaning the range of frequencies over which the peak sensitivity is almost attained. And using our results, we can actually quantify this phenomenon in more general settings. We show that the sensitivity bandwidth, delta omega, is set by the ratio between the shortest time QFI growth rate and the peak sensitivity. In the paper, we do a few different versions as well, not just focusing on a single unknown frequency. But the point is, here's one place where it turns out to be really useful to have bounds that are parametrically tighter at small times. And this is roughly because signals with possibly different time dependencies look similar at short times because not much has happened yet. So that means that a single experiment might be able to do a good job at accumulating QFI for all of these signals, whereas over large times, the states might start to look different, so you might not be able to do a single fixed experiment that works well for all of them. Okay, so to summarize, we've derived a general bound on the quantum Fisher information for systems that can be modeled by Markovian master equations. And here, this bound is phrased in terms of the time derivative of the QFI, but you can always integrate it up in whatever setting you like to get a bound on the QFI itself. And we obtained this bound using sort of a more streamlined approach that enabled a fully continuous time-dependent treatment, rather than relying on discretizing the time evolution into identical steps and analyzing each step in the same way, as done in previous work. This led to tighter bounds that are also more broadly applicable. For instance, they apply to infinite dimensional systems and or time-dependent systems. But it's also worth emphasizing that even in the more restricted settings where previous bounds do apply, our bounds are still tighter at all times. And these tighter bounds, as well as the ability to handle time dependence, allowed us to tackle other metrological questions, such as the sensitivity bandwidth question that we considered on the previous slide. Finally, we also conjecture that our bounds can actually be attained. We showed that they're tight in certain specific settings, like for a harmonic oscillator, but I think that by adapting the error correction techniques used in previous work, it might be possible to show that they're attainable more generally. So to elaborate a bit on this point, there's actually a nice interplay between quantum error correction and quantum metrology. So prior works have already considered using error correction to enhance the precision of quantum metrology. And there's even been proof of principle experiments done to demonstrate this. I also want to mention this recent work that instead of using error correction to increase the QFI, they essentially go in the other direction and use upper bounds on the QFI to infer limitations on error correcting codes. Specifically, they provide an arguably simpler proof of the approximate Easton-Nil theorem in this way. Okay, but we're only going to focus on the first direction, so using error correction to attain upper bounds on the QFI. So two papers by C.C. Zhou et al. Actually show how to achieve our QFI bounds for time-independent finite dimensional systems to leading order in T, so for large times. The first paper considers the HNLS case, where H primed is not in the Lindblad span. So once again, the magenta line here shows a bound we can derive from our general bound, and the black line shows the QFI achieved by the error correction scheme proposed in the first paper. So as you can see, it matches our bound asymptotically. This is perhaps more obvious if you look at the second plot, which plots the time derivative of the QFI. Note that the black line doesn't match the previous bound, the one in blue, but in the paper, they sort of only sought out to demonstrate that T-squared scaling is achievable. But it turns out that, by analyzing the QFI that they achieve further, the constant prefactor they get actually exactly matches R bound. And similarly, the second paper by Zhou and Zhang attains the QFI bound asymptotically for the HLS case with the right constant prefactor. Okay, but we know that the initial QFI growth rate can be faster than this eventual asymptotic rate. So these existing error correction schemes don't achieve the QFI bound at all times, whereas at finite times. Whereas on the other hand, like real experiments all take finite amounts of time. So it'd be interesting to figure out how to do things better. To do that, let's first review the existing schemes. So the basic idea of both of these two papers is as follows. So as you might expect, in addition to the detection system, they're going to use ancillas, which are assumed to be noiseless. And this is a fairly reasonable assumption because it's often the case that the detection system needs to have a specific form in order to detect the signal, and this can make isolating it from the environment harder, whereas you might be able to shield the ancillas better. So they show that there are just error correcting codes, in other words, like subspaces of the joint detection system and ancilla Hilbert space, for which the Lindblad operators Lj and the Lj dagger Lks satisfy the quantum error correction conditions, like the nil-Laflamme error correction conditions. And then they show that for any such code, the joint state of the detection system and the ancilla evolve unitarily in the code space according to this H effective, which is the projection of the Hamiltonian onto the code space. So here the pi sub c's are projectors onto the code space. And for unitary evolution, like the optimal scheme to get the largest QFI is already well known. So you prepare the initial state in the equal superposition of the largest eigenvalue and smallest eigenvalue eigenstates of the Hamiltonian, and then you just let it evolve. So then the QFI scales as T-squared with coefficients given by lambda max minus lambda min squared. Okay, so this QFI that you get depends on the code because H effective and therefore its eigenvalues depend on the code that you choose. So therefore we should optimize over all valid codes and choose the one that maximizes this eigenvalue difference. Turns out this can be phrased as a semi-definite program, and this program is actually dual. So this like maximization over the eigenvalue difference is dual to the problem of minimizing the variance of G, where remember G was like whatever was left over in H primes when we decomposed it. So like the components that we chose not to put in the Lindblad span. And as we saw, minimizing the variance of G was essentially, was precisely what we want to do at large times to get the tightest possible QFI bound. So this is roughly why their error correction scheme achieves R bound in the large time limit. But as we saw earlier, this isn't the best possible QFI growth rate at finite times. In particular, we know that the QFI can grow much faster initially. So it seems likely that by sort of modifying this error correction setup, we could achieve our bounds at all times. Specifically, I think we'd effectively want to change the error correction code with time in such a way that ends up with these schemes by Zhou and collaborators in the limit of large times. But of course, the details are to be worked out as part of ongoing work. Okay, do I still have time? Oh, really? Okay. Okay, so to just mention some other future directions. In addition to systems whose time evolution is governed by a Markovian master equation, our methods could probably similarly be applied to quantum channels. So most directly, quantum channels that are equivalent to evolution under Markovian master equation over some finite amount of time. Like even if that master equation doesn't actually describe the continuous time evolution of the system. And this might be useful for analyzing the QFI for states obtained by applying these quantum channels. Our results could also be extended by considering multi-parameter estimation problems sort of more properly. So we consider very simple examples of multi-parameter estimation, but there's much more general scenarios one can consider. And finally, a nice thing about our results, in my opinion, is that they're very general. Like they don't rely on making any assumptions beyond the setting of Markovian noise, but it might be worthwhile to specialize to concrete applications and analyze maybe actual experiments more in detail. Okay, so with that, thank you for listening, and I'll take any questions.
Great. Thanks for the nice talk, Kianna. Do we have any questions? Someone started off. Well, I'll start with a question, give people time to think. So you were mentioning applying this to some physical systems, and you mentioned some examples in the first part of the talk. So like axions, gravitational wave detection. Did you look into some more details of any of these things yet? Do you have thoughts?
Okay. Yeah, like I said, the thing I like is sort of working on a general level and not worrying about the specific details. But yeah.
And did you have further thoughts about incorporating error correction into your bounds like you were talking about at the end? Yeah,
so like I said, we can sort of see why the error correction scheme doesn't achieve the bound at all finite times, right? Because the error correction scheme that they do corresponds exactly to minimizing the variance of G, which is what gives you the QFI bounds in the asymptotic regime. Whereas we saw that in order to get the best QFI bound, we need to sort of vary G with time. In particular, we should take it to be large at finite times. So this code that they're using, basically the idea is that this maximization over the largest and smallest eigenvalues of your Hamiltonian isn't how you should find the optimal code in the case of finite times. So in order to find the optimal code in that case, we need to sort of consider a different optimization problem, which I think can be derived by looking at how we should be decomposing H primed at finite times, and then we essentially vary the code with time in this way.
Continuously in time?
Yeah, I mean, what they consider is discretizing the time evolution into infinitesimal time steps and applying error correction, active error correction, between each of these infinitesimal time steps. So, in that model, it would be a similar thing. At each time step, you might measure it to project onto a different subspace.
Interesting. Okay, great. Let's go with Dunberry.
Hey, you mentioned using adaptive methods to control. I was just wondering what you had in one case. Is that like doing measurements and then reproducing, or introducing methods to the
Oh yeah, well, you can, for instance, measure the state of your detection system at an intermediate time, and then depending on the measurement outcome, re-prepare it in a different state, or apply some kind of operation to it. So in previous metrology papers, they call this full and fast quantum control. It's kind of the same scenario where you're imagining you have the ability to do whatever you want basically between each infinitesimal time step. But for the purpose of analysis, my point was that you can phrase this as equivalence to applying controlled quantum operations and deferring all your measurements to the end, and then putting these controlled quantum operations into your Hamiltonian.
Andrew?
So thanks very much. That was really great. So I have a number of questions. So
With these error correction
Mhm.
methodology schemes, from memory, at least the original ones require this setting where there was this condition on the span of the Lindblad operators.
Oh,
That's related to the sort of things that you're talking about.
no, it's actually exactly the same. So like, I think you're referring to the first paper. And the point there was that if H primed is not in the Lindblad span,
Yeah.
then you can attain what they call Heisenberg scaling, which is this quadratic growth.
Right, and that lasts forever, whereas in
Yeah.
the normal case, you'll end up at long time.
Yeah, and the linear scaling, which they call like the standard quantum limit. So the point of the second paper is to just show that you can attain the right constant prefactor
Right.
for this linear scaling. Does that make sense?
Yeah, no, so that makes sense. And so then this analysis that you're doing is sort of saying that there's a really smooth way of interpolating between,
Or there should be,
or there should
Yeah.
be between an early time quadratic.
right?
Heisenberg scaling and late
Mhm.
time standard scaling.
Yeah, but for their linear time thing, they also don't attain the early time quadratic.
Great, more questions? Me? Yeah, go again.
I
Andrew.
was really intrigued by this bandwidth thing at the squeezing.
Mhm.
So if I want to double the bandwidth relative to coherent states, how squeezed do I have to be?
Oh,
I mean, on this plot you have squeezed.
Yeah.
So I'm wondering.
good. So basically the idea is that like, FH primed, like I said, is proportional to the variance in the momentum, right? So that quantifies how much more squeezed it should be,
Right, so I double the bandwidth by
doubling the variance. Yeah,
Doubling the
essentially,
variance.
yeah.
Okay, any further questions? I wanted to ask something about with this looking for the time-dependent optimal solution of this
Mhm.
decomposition. Did you look at some like explicit examples where maybe you attain the bound and like what do they time dependence look like in them?
Oh yeah, so like I guess the explicit example we did consider was like the oscillator example, where you just like couple it to some like external cavity past a critical time. I don't remember exactly how the details of that work, but yeah, that's like essentially doing error correction, right? Because you're like coupling it to some noiseless ancilla system and just it's like moving out some of the information. But I don't remember. I only really started looking at this when I wrote this talk.
The idea is you kind of smoothly throw terms out of the Hamiltonian with some rate.
Yeah,
Or
so
H prime, sorry.
like, I think the idea is the way that they construct these codes is in terms of what they call G-perp, which is essentially like what you get, like the component of H primes that's orthogonal to the Lindblad span. Like you put everything you can in the Lindblad span and then you're left over with G-perp. And like I said, and then like using this, they kind of, they set up their optimization over the code of the maximum eigenvalue state. But like I think you need to, phrase this problem differently and also maybe construct the code not necessarily starting from thinking about G-perp, but thinking about like what G you want in order to get the tightest upper bound on the QFI, and then consider the problem that's dual to that.